Okay, let's go ahead and get started. So, hey everyone, it's great to be here. This is a great event, and I'm just also super excited to be actually kind of rejoining the world and to be coming to events like this in person. So it's great to be here. I'm going to be talking about Bayesian optimization and Bayesian experimental design. And it's kind of difficult with an audience this large and this diverse to know how to scope a talk like this. So I tend to err on the side of giving high-level introduction and kind of intuitive high-level ideas rather than the nitty-gritty details. But if there's a group of you that want to talk about the nitty-gritty details, I'll be around all day tomorrow, and we can kind of go off and talk about those details. So let's get started. So I want to go ahead and try to motivate Bayesian experimental design, Bayesian optimization. And the motivation here is that numerous design problems spanning the sciences, engineering, machine learning, and beyond, they all suffer from these prototypical challenges where you've got maybe this enormous design space, so that all the possible configurations you could configure your system in, and where that design space is inherently slow to explore. So maybe investigating a particular configuration requires doing, say, an experiment in a laboratory, or running maybe an expensive computer simulation, or getting a human involved, something like this. So now you've got this big space, and you're very limited in terms of your bandwidth, your ability to explore that space. And so you're left kind of searching for needles in a haystack. Experimental design as a field got its start in crop breeding. So this is a situation where these two problems are really highlighted. Let's say that you're trying to maybe design a corn hybrid or something like this, where you want to, say, maximize yield as a function of the genome of the plant. Here you've got the design space as the entire genome, which is this enormous space. And you may only get to run one experiment a year. You get to maybe decide upon some hybrids to cross, and then you plant them in the ground, and then you wait a whole growing season, and then you can see how tall they grew, and then you can start to plan your experiment for the next year. So now this is exactly this kind of searching for a needle in a haystack kind of problem. This is a problem that mankind has been facing since the dawn of agriculture. Okay. Now, the Bayesian approach to experimental design has really found a niche in accelerating discovery and design in these kinds of situations. And Bayesian optimization in particular is one popular realization of this paradigm that's made a lot of inroads in the sciences and engineering and beyond. I recently wrote a book on Bayesian optimization, I literally got my first copy last week, so it's actually available. But it's also available for free to download at bayesopbook.com. I'm going to be, again, trying to give the high-level ideas in this talk, but I do have some pointers to material in the book where you can find my take on it and also pointers to other people's takes as well. OK, so before we talk about the details here, I need to establish a common language and just some groundwork. What do I mean by experimental design? Well, central to any experimental design problem, there's going to be some mapping from some design space to some properties of interest. So the design space is going to be all of the things about an experiment that we can control, all the configuration that we can do. And then the properties of interest will be anything we can measure about the outcome of an experiment after configuring it. Just to give a couple of examples, in machine learning, we might have an experimental design problem where, say, we're trying to configure a deep neural network or something. We want to tune its hyperparameters. So all of the set of hyperparameters would be the design space. And then maybe we might want to map that onto some properties of interest, like the validation error of the network after training. And so our goal would be to try to minimize, say, the validation error as a function of the hyperparameters. In the context of something like material science, maybe the design space would be the composition of a material and the processing parameters under which we synthesize it, like temperature and pressure and things like this. And that's going to map onto some material properties that we can measure after synthesizing this material. So that could be optical properties or mechanical properties like strength and ductility and things like this. Again, we're mapping from the design space to these properties of interest. Now, in addition to having an experiment that we can run, we need to have some goals in mind. If we're going to be thinking about the design of experiments, we need to be cognizant of what our goals in running an experimental campaign are. It's hard to talk about this in generality because the details are going to vary from situation to situation. But I can at least identify some typical high-level goals that we might have in conducting a sequence of experiments. The simplest of which might be that I simply want to learn this mapping. So maybe I want to conduct a sequence of experiments so that given any point in the design space, I can make accurate and confident predictions about the properties of interest. So I simply want to do learning. In many other situations, I might want to optimize the properties of interest. So maybe I've got the surface that is the property of interest, and I might want to say find the strongest material or the best possible validation error over the design space. So that's like an optimization problem. Or maybe I want to try to find novel configurations, as many as possible, that satisfy some properties of interest. That might be like a discovery problem. I'll talk more about that later on in the talk. And of course, sometimes maybe I want to do some variation on these or a combination of the above, and that's OK, right? I just wanted to seed in your mind the kinds of goals we might have in conducting a sequence of experiments. And so now Bayesian experimental design can address all of these goals and more. And so for each of these kinds of paradigms, it will map onto a particular kind of subfield of Bayesian experimental design. If I want to do just learning, learning this mapping, that will map onto Bayesian active learning. I want to do optimization, that maps onto Bayesian optimization. And if I want to do discovery, that maps onto something called active search. And I should say, like Bayesian optimization, Bayesian active learning, these are not like algorithms per se. It's more like a philosophical approach to learning and optimization that are all tied together through the mechanics of Bayesian inference. In this talk, I'm going to be mostly focusing on the optimization and search side of things, because this is kind of where I think the challenges become most compelling, and this, it's a lot of buy-in from various subfields. OK. So first, I'm going to just give a high-level introduction to the main ideas in Bayesian experimental design, and then we're going to identify some components of interest, and then we'll dive deeper into those as the talk progresses. So if there's just one slide to remember, it's this slide. This is the basic idea, the central idea in all of Bayesian experimental design, which is that we're going to be conducting a sequence of experiments, and we're going to do so by following this feedback loop on this slide. So at any point in the sequence of experiments, we'll have some observed data. This will be like the outcomes of experiments that I've already run. And now I'm going to use that data to train a model. And the job of the model is going to be to predict the outcomes of proposed experiments in light of my experience. Now I'm going to take that model. I'm going to go over my design space. I'm going to make predictions about the outcomes of these experiments. And then I'm going to use those predictions in combination with my goals to, in some way, design some experiments. I'm going to hand them off to somebody in the laboratory. They're going to run an experiment or whatever, right? I'm going to get the answer back. I'm going to add it to my data set. I'm going to retrain my model. I'm going to make new predictions, design more experiments, and continue in this loop as until I get tired, or my grant money runs out, or I decide I'm done. So in this loop, there's only 2 points, really, that I can make any influence over what happens. The first one is in this modeling step, and then the second one is in the experimental design step. I'm just going to give you a high-level intuition about what happens in each of those boxes. So in the first step, modeling experimental outcomes, this is kind of like the key idea in all of Bayesian experimental design, is that I'm going to be maintaining a model of the properties of interest over the design space throughout experimentation. This can take many forms. Was plotted up here as a Gaussian process. I understand that many of you are familiar with Gaussian processes. Also, we had an excellent introduction earlier today. But in general, we're going to have this model that's going to somehow yield predictions, like point predictions over the design space of the properties of interest, with some quantified uncertainty, which would be like the width of these error bars. So we're going to begin with a prior, and then as we gather more data, as we run these experiments, we're going to be conditioning that prior on those observations, maintaining a posterior belief over the properties of interest throughout the process. OK, so now how do we actually design experiments? Well, we're going to be using the predictions of that model. And again, we're going to be combining that with our experimental goals to design a policy. So the way Bayesian experimental design usually plays out is that we're going to be using the model to derive and optimize a score function over the design space. That score function is also called an acquisition function because it tells you what data you want to acquire. And the role of the acquisition function is to somehow quantify how useful a given experiment would be for achieving our experimental goals. And then optimizing that acquisition function is going to tell us which experiments to run next. OK. So I'm going to give an example here, a couple examples of Bayesian experimental design. We're just going to see it running and the kinds of behaviors that that might come out. So at first, let's just imagine that I want to learn this mapping from the design space to the properties of interest. So a kind of policy you might come up with for designing experiments that you could do with just purely intuitively without knowing anything at all about Bayesian experimental design might be to say, OK, I have this model. The model's making predictions of the properties of interest. The model's producing this quantified uncertainty in those predictions. And if my goal is to try to decrease my uncertainty over time, then how about I just conduct the experiment with the widest at the point in the design space where I'm the most uncertain. So we can accomplish that by defining an acquisition function, which is this green surface underneath the model here, which is simply the width of those credible intervals of the model. And now I'm going to design experiments by maximizing that acquisition function. And so we're going to see a demo of this working. What we're going to see here is we're going to see this model of this function. The red function is the ground truth. It's just there that I used it to simulate the experiments. It wasn't known to the algorithm as it was progressing. And the tick marks underneath the model are going to show a sequence of 19 experiments that are designed by sequentially optimizing that acquisition function, making a measurement, and then updating the model. And we're going to see some snapshots of the model's beliefs over as this process continues. And what we see is that for this particular acquisition function that's trying to always try to collapse uncertainty as much as possible, then we get this nice emergent behavior where the experiments kind of automatically produce this kind of space-filling design. At termination here, we've collapsed the uncertainty. We now know most of the function values here with some degree of confidence. OK, but what if I have a different goal in mind? What if I want to do optimization of this function? So now I face this tension of exploration versus exploitation, this kind of classic trade-off in experimental design, which is that every time, so if my goal is to, say, maximize this function, then every time I design an experiment, I have to reason about whether I want to evaluate the function somewhere where I believe it's going to yield good properties, like where maybe my posterior mean of my Gaussian process is high, or if I want to still measure somewhere relatively unknown. So this first case of trying to make a measurement where the posterior mean is relatively high, that's called exploitation. And it can be a useful action to make because it can lead to immediate improvement. Maybe I can find like a higher function value than I've seen previously. Whereas exploration can help enable future improvements. So if I explore somewhere relatively uncertain, then either I could find maybe a surprisingly high value, which might lead to further investigation in that region, or I might not see anything interesting, in which case at least I now have that knowledge to help guide future experiments. So I've got this classic trade-off between exploration and exploitation. And it turns out to do optimization effectively, I need to very carefully manage that trade-off. And so the key idea in Bayesian optimization is to try to somehow construct acquisition functions that think about this trade-off. And so here I've got an example. Again, I've just got this. It's just the Gaussian process model conditioned on 3 experiments. And now we're going to see this green acquisition function here. We're going to see it 3 times in this talk, each time with a new layer of understanding of exactly what's going on. But for now, we can just imagine that it's somehow been constructed to reason about this trade-off. Now, compared to the previous example we saw, it both rewards exploration. Like if you look where there's a high degree of uncertainty in the function, there's still a relatively high value of this acquisition function. But now the regions around these local optima on the right-hand side and there's one on the left-hand side now have a boost, which is now also encouraging exploitation. But I can still design a sequence of experiments by computing this new acquisition function, maximizing it, and then updating the model, et cetera. And if I do so, then I'm going to have like a totally different quality to the experiments that I'm going to design. And again, we get this really nice emergent behavior. So here, this is the same demo as before. It's the same ground truth. It's the same model. The only thing I've swapped in is this new acquisition function. And now we're going to see totally different behavior in the experimental design. Now, the first two experiments, instead of measuring over on the left-hand side here, they now are designed, they're focusing on exploitation. They're mapping out this region around this local optimum I started with. But at some point, like after those two experiments, the uncertainty in that region is kind of collapsed. And the algorithm decides there's nothing else to learn there. So then it switches to this other local optima on the left. It actually designs the next 10 experiments in that region, discovering the global optimum on iteration 7. At some point, it still decides in that region there's nothing left to learn. It kind of collapses that uncertainty, at least in the regions that are most interesting. And then it kind of automatically switches to exploration. So the next 7 experiments here are designed to collapse the remaining uncertainty in these unexplored regions. And now at termination, we have a totally different set of experiments. Most of our observations were near optimal. Like they're all actually higher. The vast majority of them resulted in observations that were higher than the prior mean. And the optimum is known with confidence. Like if you kind of look at the credible intervals, there's no region in the design space here that could plausibly be the global optimum. Like the upper confidence bounds are all lower than the best point that I saw. And as we're going to see, this kind of different types of behavior in experimental design is going to just happen automatically by turning a Bayesian crank that I'm going to outline for you. OK, so I want to address some caveats here, which is that Bayesian experimental design is not always a good idea. And the reason for that is that accomplishing this kind of system that I've outlined here requires a lot of work. So there's work in building and validating and maintaining this model of the properties of interest throughout experimentation. There's also work and then like deriving this acquisition function and optimizing that acquisition function. So if you can afford like millions of experiments, you probably, this is probably going to be a waste of your time. However, if you're in this kind of regime where experimentation is very expensive, then the payoff for this investment is unparalleled sample efficiency. So like Bayesian optimization in particular can be easily dozens to hundreds of times faster or more efficient than alternatives like random search. The table here is from this Numerics. There was a competition at Numerics 2020, this black box optimization competition. And the way it worked was that teams could submit algorithms of any design that they saw fit that would then be presented with these black box objective functions that they would interact with some kind of API where they could specify points they want to measure, and they would get back these measurements of the function. And there was this high-profile paper that was trying to make claims that Bayesian methods were no better than simply running a bunch of random searches in parallel. But it turned out here, one of the ways they measured performance here was via this right-hand side, this column on the right here, the random search efficiency, which was computing the number of random searches you would need to be running in parallel with the same budget as the algorithm used in order to achieve the same performance and expectation. And the winner here from Huawei was like over 100 times more efficient than random search under that measure. And all of the top of the leaderboard here were in fact using Bayesian methods. OK, so we've got this loop. And I'm now going to kind of dive into some of the components into more depth. So the first one is this modeling step. Thankfully, again, we had an excellent introduction to Gaussian processes, so I don't need to go too deep there. But I mostly want to address the fact that sometimes we don't necessarily need to use a Gaussian process. So this kind of idea of modeling the properties of interest and maintaining this probabilistic belief, this is the key idea in all of Bayesian experimental design. Gaussian processes are extremely convenient here, both in terms of building expressive models and also just mathematically convenient for inference. They're by far the most common choice in Bayesian optimization, especially when you're in a situation where you're kind of stuck in the small data regime. So if you're in a situation, I often work with collaborators that come to me only being able to make maybe 20 measurements of their system a year, in which case they're never going to have enough data to train a sophisticated model. And Gaussian processes tend to be a very good off-the-shelf solution for this kind of situation. But of course, using a Gaussian process is not mandatory for Bayesian experimental design. Bayesian optimization has been successfully used with other alternative models, random forests, neural networks, Bayesian neural networks, et cetera. In some cases, you might be able to build like a really sophisticated model, like a physics-guided neural network or something. That would also be an excellent choice. And a recent innovation that's been making a lot of inroads in certain situations, and especially, for example, like molecular design or gene or protein design, where the design space is naturally discrete. So either like a large space of molecules or these like gene and protein design is effectively optimization over a high-dimensional string. Then there's been a lot of inroads in terms of building continuous representations of these discrete design spaces using something like a variational autoencoder or some other kind of neural representation technique that will then map you from this discrete space of alternatives to a nice continuous space to work in. And we can do our modeling there. And then every time we design an experiment, we'll just like map the point through a decoder to tell us which molecule or which gene sequence or protein sequence to amino acid sequence to synthesize next. And so like this kind of idea of using Bayesian optimization in these latent neural spaces has really helped in some very challenging optimization problems. OK, so now let's talk about building a policy, which is the step here. So recall, a policy is what's going to map us from our beliefs over the properties of interest and our experimental goals onto experiments. There's a few different ways to make a design a policy in Bayesian optimization. I'm going to talk about an alternative in a little bit. But here I'm going to focus on Bayesian decision theory, which is both a common approach in policy design and is also a very natural one when we're doing this Bayesian modeling. So the key idea here is to define something called a utility function, which is going to quantify how useful a given set of experimental results would be in retrospect. So the utility function is going to take in a data set that's already been collected, and it's going to assign it some score that is commensurate with how useful it was for our experimental goals. And the purpose of the utility function is to quantify our preferences of our experimental outcomes, whereas the model is going to be representing our beliefs over experimental outcomes. The utility function is going to summarize our preferences. And so in these demos we had earlier, the only difference between them was the choice of underlying utility function. So depending on my goals, I can design the utility function to reflect those goals. So in the top there, I was using a utility function that was rewarding reduction in uncertainty. And in the bottom, I was using a utility function that was rewarding identifying high values of the function of interest. And so you can see those preferences between either reducing uncertainty or maximizing this function in terms of the data that was gathered. Like in particular, the bottom situation, found optimal values of the properties of interest, but it left kind of large regions where I was relatively uncertain. And so it's the goal of a utility function to identify which of these two situations I would prefer. OK, so at its heart, so in Bayesian decision theory, is a framework for making decisions under uncertainty that's extremely general, that could be effectively applied to any such situation. But at its heart, it's really actually quite simple. So once I've identified a utility function for whatever situation I'm in, then I'm going to choose the action that is going to maximize the expected utility resulting from that action. So, right, because again, like the utility function is going to be assuming, in the context of experimental design, the utility function is going to be quantifying how useful a data set is in retrospect. And here I'm going to be taking an expectation with respect to anything that's unknown. In particular, the outcome of my decision. So in the context of experimental design, the key unknown information that's going to appear in this computing this expectation, the expected utility, is going to be the outcome of the experiment that I'm proposing. This is the whole point of modeling the properties of interest, is to be able to compute that expectation. So now I'm going to be like the optimal experiment to design in this framework of Bayesian decision theory is simply going to be the experiment that maximizes the expected utility of my data after running the experiment. Or maybe after running a sequence of experiments. And so with this extremely hand-wavy introduction to Bayesian decision theory, we're actually prepared to create a policy for experimental design. We're going to create an acquisition function that is the expected utility from adding a proposed experiment to my data set. And then I'm going to run the experiment with the highest expected utility. So here, this is the second time that we're seeing the same acquisition function, but now we have a new understanding for how this utility function, or for how this acquisition function is constructed. This green curve was constructed by computing this expected utility for a particular utility function. And now, when I'm maximizing that acquisition function to design an experiment, I'm taking this argmax of the expected utility over the design space. OK, so I want to inject an idea here, which is this idea of non-myopia that we're going to get to a little bit later on in the talk. So theoretically, if I'm conducting a sequence of experiments, then the optimal thing to do from the point of view of Bayesian decision theory is to maximize the expected utility of my data that's going to result at the end of the entire experimental campaign. And so if I know, say, that I'm going to be running 100 experiments, and I've run 50 already, then in designing the 51st experiment, I theoretically need to be reasoning about its outcome, but also how its outcome is going to influence the design of the 52nd experiment, and where that's going to be, and what its outcome is going to be, and then how that's going to, et cetera, all the way to the end of the experimentation. So I've got, theoretically, I would like to be able to compute this expected utility by computing this, like enumerating this enormous decision tree that's going to have a branching factor for every measurement and every experiment from now until experimentation is over, which becomes, very, very, very quickly out of hand, because the branching factor in each of these decisions is absolutely enormous. And so as a result, especially in Bayesian optimization, we have to make an approximation to that, full look-ahead expected utility by just looking a few steps ahead. And in particular, in Bayesian optimization, it's very common to simply look one experiment ahead. So to design experiments that will greedily optimize the marginal increase in the utility by just moving one step into the future. That's an approximation known as look ahead or one step look ahead, or sometimes it's kind of disparagingly called a myopic approximation, because I'm only looking right in front of me instead of all the way to the future. OK, so let's consider an example from optimization. So the simple reward utility function is a utility function that is effectively the highest property value that I've seen. So I need a utility function to measure progress in experimental design. Here I'm simply going to say, if I want to optimize the function, then I will score a data set according to the highest value in the data set. So for this particular example, the value of this simple reward utility is going to be the height of this red dashed line here, which is, for this data set, the highest value that I saw. It's a natural utility function, I think, that you might come up with for measuring optimization progress. And now if I want to compute one-step look ahead, if I want to compute a one-step look ahead expected utility with this utility function, then this is how it's going to play out. So I've got this belief. I have like the utility of my current data set, which is the height of this dashed red line. And now let's say I consider adding an observation at this point x. So I've got a belief about the function. Oh, I'm dragging around the mouse as if I could point at things, but it's actually not reflected on the screen. So the point x is the optimal point where the triangle is. That's where the next experiment is going to be designed. And now there's this Gaussian process. There's a Gaussian belief about the function value at that point, which is a relatively high mean, relatively lower uncertainty. An alternative point would be this point x dash on the left-hand side, where there's a relatively lower mean but a relatively higher uncertainty. Right. Now, if I make a measurement at either point, there's two things that could happen, right? So either I'm going to see a function value that is higher than the best function value I've seen thus far, or I'm going to see a value that's lower than the best that I've seen so far. So if I see a function value that's lower than that dashed red line, then I'm not going to improve this simple utility at all. Whereas if I see a function value that is higher than that dashed red line, I'm going to make a linear improvement to that utility function. In the lower left, I have a plot. This is now basically, this is the y-axis, and the upper plot has now become the x-axis. The tick mark along the x-axis in the lower left is the height of that dashed red line. That's the utility of my current data set. The red curve, the piecewise linear red curve in the lower left, is showing the increase in utility that would occur when moving from my current data set to a data set with one more data point inside of it as a function of what the measurement I make is. And then finally, the two Gaussian distributions, because I have a Gaussian process, are showing my belief over the outcomes that would result if I made a measurement at either x prime, that's the wider but shorter distribution, so it has a lower mean but a higher uncertainty. And then the darker distribution is my belief at x, which has a relatively higher mean, relatively lower uncertainty. And now to compute this green curve, to compute this acquisition function, I'm going to be taking an expectation of the improvement in the utility, which is the piecewise linear function, with respect to these Gaussian distributions. And just eyeballing it, you can kind of see that the darker distribution is going to have a higher expectation because it has more mass in the region where I'm making improvement. And that's reflected by the fact that the green curve is higher at x than it is at x prime. And in fact, the way this green curve, this is the third time we're seeing this function now, is computed at any point is by taking an expectation of this piecewise linear improvement in utility with respect to the Gaussian distribution associated with each of those points. OK, but so that was all very mechanical. We're computing a bunch of expectations of Gaussian beliefs against these piecewise linear functions. But the really cool thing here is that this gives rise to this emergent behavior that we saw before. So we have this algorithm that just by inspecting its behavior is doing this really careful balancing of exploitation and exploration. It does a great job, like a very nice efficient job of optimizing this function, but underneath the hood, it's really just all mechanical. It's just following a very simple recipe for experimental design, which is outlined on this slide. So if I want to use this Bayesian decision theoretic method to design experiments, then here's a recipe I can follow. So there's kind of two steps I need to do at the beginning, which I can do in either order. The first one is to choose a utility function that is somehow going to encapsulate my experimental goals. And then the second step is to identify my design space and model the properties of interest. And now to design experiments, I will compute the expected utility of every possible experiment in the design space with respect to my current beliefs. And then I'm going to run the experiment with the highest expected utility. I'm going to add the outcomes to the data set, update the model, and then I'm going to continue on in this loop until I decide that I'm done. This is just the same feedback loop that we saw earlier, but now kind of written out as a procedure. And now, fortunately, building this kind of system is relatively simple these days because there's really sophisticated software available. GPyTorch and BowTorch, for example, are both built on the PyTorch infrastructure. So there's all this, all kinds of automatic differentiation and all this stuff is all built in. The GPyTorch developers have spent and all received shout outs in John's talk earlier this morning. They've also thought really deeply about sparse approximations and numerical efficiency and scaling to really large data sets and using GPUs and all that kind of fancy stuff. And so you can take the software off the shelf and you can build pretty sophisticated Bayesian optimization routines on top of them with relatively little work. OK, so we have this Bayesian decision theoretic approach to experimental design by computing expected utilities and maximizing them. I want to give a few examples of utility functions that are used in optimization and policies associated with them. So it turns out that humans are really bad at understanding their preferences. They're also really bad at understanding their beliefs. And it can be challenging to come up with utility functions that are truly reflective of your preferences, especially when you have maybe multiple competing objectives. But fortunately, there are kind of nice utility functions that are available off the shelf that you can use in certain situations. And then performing one-step look ahead with those utility functions, so greedily maximizing the marginal increase in utility, yields commonly encountered policies for Bayesian optimization. And this link between the underlying utility function and then the acquisition function that is the expected utility is sometimes missing in the literature. So I just want to kind of map this out. So the first example we've seen already, which is this simple reward utility function. It's a very natural utility for optimization. It's simply quantifying the highest function value encountered during optimization, as measured by the posterior mean. Or you can also reinterpret this as the expected utility of an optimal risk-neutral recommendation after optimization. So if you're reasoning about optimization as a procedure that's going to gather data that is going to support the recommendation or the identification of a particular point in the design space for use in, say, a production system, then this might be the kind of thing you might want to reason about as your performance on this final recommendation, which is itself a decision that you might make by Bayesian decision theory. And so for this particular utility function, if I compute one-step look ahead, that gives rise to an acquisition function known as expected improvement, which is by far the most common acquisition function encountered in Bayesian optimization. But an alternative is the so-called global reward utility function. So whereas the simple reward utility function is only giving credit for finding higher values of the function at locations that you measure during experimentation, And like another way to think about that is that you're restricting this final recommendation to only the points that you measured during optimization. But if we allowed ourselves to relax that to say, OK, I'm going to think about the ability to recommend points, any points in the domain, in a risk-neutral manner, rather than just the points I measured, that's going to lead you to this global reward, which is going to be the highest function value anywhere in the design space, again, as quantified by the posterior mean. And now one step look ahead with this utility function yields a policy known as the knowledge gradient. I've got the knowledge gradient acquisition function plotted here for the same model that we've been seeing throughout this talk. And there's actually a pretty cool thing that happens here. So when I first made this plot, I thought I must have a bug in my code or something, because here the policy is recommending that we make a measurement that's right next to a measurement we've already made. So like the uncertainty at this point that's selected, marked by the triangle, is quite small, which seems like ridiculous to me. Why would I want to do that? Well, there's this kind of cool emergent behavior again that is appearing here, which is that if I'm going to allow myself to kind of claim some reward for increasing the posterior mean anywhere in the design space, then you might reason as follows. So you say, OK, I have this measurement on the right-hand side there. It's kind of off in the middle of nowhere. It's a relatively high value. It's very unlikely that the local optimum of the objective function is going to be exactly where I measured, right? So instead you might say, well, OK, probably there's going to be like a local optimum on the left or the right at that point. And if only I could know the derivative of the function at that point, I would know. Like if the slope were negative, then there would be a local optimum to the left at that point. If the slope were positive, then there would be a local optimum to the right at that point. And I could use like the smoothness properties in the prior here to infer with a high degree of confidence where that local optimum would lie if only I would know the derivative. That idea is like plotted in the lower right here. So this is showing like samples of what the updated posterior mean of the function would be for various potential observations at the marked point. And you see, depending on the implied slope, we have a new local maximum of the posterior mean on the left or the right. And so what's happening is that the policy has kind of automatically learned to use a finite difference approximation of the derivative at this point in order to infer if the local optimum is located to the left or the right. Whereas expected improvement looks like this. Because it only ever captures reward if it improves the function value at a measured location, it kind of has to guess if the local optimum is to the left or the right and hope that it's right. If it turns out that the slope is wrong, it's going to have to make a measurement on the other side. So this global reward can kind of be a little bit more efficient by allowing you to capture this reward without really making a measurement there. OK. An alternative, another utility function that's used, has been used quite effectively in optimization is known as information gain. This is an information theoretic utility function that is trying to measure how much I've learned about some random variable as a function of some data set. In the context of Bayesian optimization, I might say, well, I'm trying to find the optimum of this function. So maybe I want to try to increase the information that I know about its location. Or maybe I want to try to increase the information I have about the value of the optimum. Here I'm showing a Gaussian process. And now by choosing this prior distribution on this objective function, I induce a belief about the location of its optimum, which is the distribution beneath the function, the model here. I also induce a belief about the value of the optimum, which is on the right-hand side over there. In this case, I'm relatively uncertain about the location of the optimum. We've got this, quite a lot of probability mass spread all over the x-axis. There's also like these point masses right on the boundary. And then there's also a fair amount of uncertainty in the value of the optimum on the right-hand side. And now I could say, well, if I want to try to increase my information about these things, then maybe I will score a data set according to how much it was able to reduce the entropy of these distributions. So their ability to increase the information that I have about those quantities. If you don't like what I just said in terms of differences of differential entropies, you can also swap in the KL divergence between the prior and the posterior. It turns out you'll get the same thing in the end. And so now, for either definition of information gain, if I perform a one-step look-ahead expected utility computation, that's going to yield an acquisition function known as mutual information, which is also a central concept in information theory. In the context of optimization, this phrase of entropy search is very often used for methods that reason in this way. There's both entropy search, which is trying to maximize the information about the location of the global optimum. There's also something called max value entropy search, which is trying to maximize the information about the value of the optimum. And both of them so this is just a demo of an entropy search method. It makes a bunch of measurements. Again, there's a clear trade-off between exploration and exploitation. Here, the uncertainty in the location of the optimum, the location of the optimum has collapsed to this almost point mass. Similarly, with this max value optimization, again, we see nice emergent behavior of exploration versus exploitation, and it's collapsed the uncertainty in the value of the optimum to basically a Dirac delta. But the nice thing about mutual information is that I can swap in any random variable that I want to learn about. I don't have to choose a random variable that's associated with optimization. So in these entropy search methods, I'm usually finding some induced belief about something to do with the optimum of the function. But I could, if I just want to say learn about the function itself, I can also use mutual information. And in fact, this demo that we saw earlier of just this pure learning algorithm that was trying to reduce uncertainty, that was accomplished by sequentially maximizing the mutual information between the measurement and just the function itself. So this Bayesian experimental design by maximizing mutual information is an extremely powerful and generalizable idea. In fact, it goes back to the 1950s, to Dennis Lindley, who proposed this as general purpose Bayesian experimental design. And you can regard this as kind of a mathematical realization of the scientific method. Like, I'm trying to learn about something, I'm maintaining a belief, and I'm always going to be conducting the experiment that's going to challenge those beliefs as much as possible. OK. I want to say a little bit about computation. So there's something that I've been hiding under the rug for quite a bit now, which is that this kind of conceit in Bayesian optimization, which is that I began with an optimization problem. I want to try to find the global optimum over the design space of this property of interest. And I'm trying to solve that by another global optimization problem, which is maximizing this acquisition function, which if you just look at this particular example, it's got, it's a multimodal non-convex function. So how did I make my life at all any easier by reducing optimization to optimization? Well, the key is that in Bayesian optimization, we usually assume that experimentation is extremely expensive, and maybe I can't, usually I can't get any insight into the derivative unless I do a finite difference or something like that. Whereas the acquisition functions that we derive in this Bayesian decision theoretic framework or some other framework are usually very inexpensive and differentiable. And so we've reduced optimization of an expensive non-differentiable function to the optimization of an inexpensive differentiable function. And so we can use off-the-shelf methods to exhaustively optimize them. And so all of these policies, for all these utility functions, I can either exactly compute this expected utility, or I can at least approximate it effectively, yielding effective algorithms. OK. So for this audience, I also want to talk a little bit about theory. Again, I'm going to try to do so in a way where I just give some high-level ideas rather than any details. We'll see how effective we are. So in the previous two sections, we talked about Bayesian decision theory as a mechanism to design experimental policies. Here, I'm going to talk about bandit-inspired policies. So multi-armed bandits, is a field of research that goes back to the 1930s, exploded in the 1950s with a whole bunch of very strong theoretical results. And over the years, these very strong theoretical results that are known for multi-armed bandits have been very tempting in terms of identifying those algorithms and maybe trying to borrow their ideas to establish theoretical guarantees for Bayesian optimization. So I should say that these decision theoretic approaches that I mentioned, expected improvements, entropy search, things like this, they tend to have the superior small sample performance. But they are also have been somewhat challenging in terms of establishing strong theoretical guarantees. OK, so multi-armed bandits are just like a kind of model problem in sequential decision making under uncertainty. The kind of prototypical multi-armed bandit, you've got some discrete set of alternatives or arms. Each one of them has got some reward distribution associated with it. We usually assume that these reward distributions are conditionally independent given the selection of the arms. And the idea is that you want to find an adaptive policy to select a sequence of these arms, observing the associative reward in order to maximize your cumulative rewards, like the average function value that you see over time. In order to do so effectively, again, you need to balance exploration versus exploitation very carefully. You need to explore all the alternatives sufficiently so that you kind of convince yourself that you're not missing out on some superior arm that you may have ignored. But also, you need to make sure that over time you're allocating more and more resources to the arm that is actually optimal in order to do so effectively. And the nice thing here is that there are very simple policies for multi-armed bandits that have very strong theoretical results. And this has been the case for many decades now. And so now the idea here is that maybe we can model optimization as like an infinite arms bandit. So we've got this design space. We can think about every point in the design space as being an arm. We can think about that arm having a reward distribution associated with it, which is like the belief of my Gaussian process. Now, unlike in the multi-arm bandit case, my rewards are actually correlated over the arms. If I make a measurement at a point, I'm going to learn about nearby arms. But I can also think about, again, trying to find an adaptive policy to maximize the cumulative reward. And it turns out that we also, in this case, have developed efficient policies that also have strong theoretical results, basically by taking borrowing the policy from the multi-arm bandit case and adapting it to this infinite arm correlated setting. So I'm just going to give two examples. The first one is the upper confidence bound algorithm, which is going to maximize some statistical upper bound of the objective function. In the case of a Gaussian process, that is as simple as taking the posterior mean plus some number of posterior standard deviations. For this particular example, that would lead me to measure at the point maximizing this upper envelope, which is the point on the right-hand side there. This is kind of an encapsulation of this general idea of optimism in the face of uncertainty. Another algorithm that goes all the way back to the early 1930s is Thompson sampling, where just like in entropy search, I can think about this belief over the location of the optimum. Whereas in entropy search, I was trying to greedily maximize the improvement in my understanding of that distribution. In Thompson sampling, I simply take a stochastic approach, and I'm going to just sample from that distribution and make a measurement wherever that sample happens to be. But again, I'm going to be allocating more resources to the points that are more likely to be optimal, so it's a reasonable idea. And in the case of optimization, both of these algorithms enjoy very strong, in some cases near optimal, theoretical guarantees. So I'm just going to sketch the key ideas behind these theoretical results. The first one is like how we're going to quantify our goals here. Well, usually what we do is we try to seek we seek to bound the asymptotic growth of the so-called cumulative regret. This is just for every observation I make, yi, I'm going to measure the difference between my observed value and the globally optimal value. That's known as the instantaneous regret. And then the cumulative regret is the sum of this over all of my iterations. If this cumulative regret grows sublinearly, then the conclusion I can draw is that all observations that I make are going to be eventually effectively near optimal. Like in order to, if you normalize this cumulative regret by dividing by n or something, then what we're going to see is that my average function value that I'm observing is going to converge to the global optimum. And so by reasoning about the asymptotic growth of this cumulative regret, I can conclude A, that maybe I converge to the optimum, and B, some rate at which that convergence happens. In order to proceed, I need to come up with some kind of notion of regularity. It turns out that if you want to say something like that you're going to converge for all continuous functions or something, that's way too weak, because an adversary could always construct continuous functions that would have like these needles, these like spikes, really, really tall spikes that are really, really narrow that you'll never find. And so in order to have some meaningful convergence rates, we need to establish the feasibility of optimization to begin with. In Bayesian optimization, there's a couple ways I can go. If I wanted to do like a Bayesian analysis, I might assume that my function is like a sample path of the Gaussian process prior that I'm using to model it. If I'm taking a frequentist analysis of the Bayesian algorithm, I might assume that my objective function is some element of some reproducing kernel Hilbert space associated with my GP prior. And now the kind of typical strategy to bound the cumulative regret is to establish some concentration property for the posterior distribution. For example, a typical path that we might take is to try to seek some sequence beta t of like confidence multipliers. And I want to try to construct this sequence such that I can prove that the objective function is always, with high probability, inside of the confidence region mu t plus or minus beta t sigma t. So basically, I want to show that with high probability, it is always the case that my objective function, the red curve on the lower left here, is always contained inside of this uncertainty envelope. And if you can somehow find such a sequence beta t, then analyzing the upper confidence bound algorithm is actually really straightforward. And the key observation is that if you can construct this sequence, and if you know that the function is always inside of these confidence regions, then we can conclude that the optimum of the function is always inside of the confidence region for every selected point. And so why is that the case? Well, if the confidence region for the global optimum were up here, then I would have selected that point instead. And if it were down here, then this point would have been optimal. So it's really easy to reason via contradiction that this must be the case. And now if you've got this property, then this cumulative regret can be bounded by the sum of the widths of the confidence intervals for the points that I select. So then it all comes down to the properties of this sequence beta t. What you would really like to be able to find is you'd like to be able to find a very slowly growing sequence such that the sum of the widths of these confidence intervals is relatively small. And it turns out that for Gaussian processes, you can bound the cumulative regret in terms of something called the information capacity of the process, which is like the maximal information gain for some sequence of noisy observations. And useful bounds for this information capacity are known for like very useful kernels, in particular the Matern family and the squared exponential kernel. And then you can use those bounds on this information capacity to derive strong asymptotic bounds for the performance of the UCB algorithm and Thompson sampling, in both the expected case and the worst case. And when I say strong asymptotic bounds, at least in some cases, these bounds are near optimal in the sense that they are within logarithmic factors of corresponding lower bounds that apply for any algorithm. OK, so if you want more information, the gory details of all of this are in chapter 10 of the book. I'm only just scratching the surface here. OK. Now I'm going to switch gears and talk a little bit about a problem that I've also personally worked a lot on, which is called active search. It's related to Bayesian optimization. And so the way to motivate this is that if you imagine that your design space is this ocean, and there's this function that is the properties of interest, then if we think about the ocean as being some level set of that property of interest, and that rising above the ocean are these little islands, which are kind of like regions of the design space where these configurations are exhibiting desirable properties, then Bayesian optimization would be trying to find the point in the design space that has the highest peak, whereas active search says that anything above the water is interesting, and it wants to try to map out all the islands. So this is really meant as a mathematical model of scientific discovery. So we imagine that we're conducting a sequence of experiments where we have some binary condition indicating success of an experiment. For example, in drug discovery, I might define success as saying that some molecule that I'm investigating exhibits sufficient binding activity to some protein or something to warrant future investigation. Then the goal of active search is to find as many successful experiments as possible inside of an experimental budget. So a real-world example of an active search problem is this board game Battleship, or Schiffe versenken. Heißt es auf Deutsch? So here we have a design space that is literally an ocean. It's this 10 by 10 grid. And I can conduct a sequence of experiments to reveal either hits or misses. And I want to design my experiments sequentially so as to recover as many hits as possible in a given budget. Now, if you've played this board game, especially if you played this board game as an adult against like a small child, you very quickly realize that there's an optimal policy for Battleship that involves trading off, like constantly switching between exploration and exploitation. You kind of want to map out the ocean, and then every time you find a new ship, you kind of switch to exploitation, and then you switch back to exploration. OK. So for this problem, there's a very intuitive, again, like an algorithm that you could come up with that if you've never, even if you don't know anything at all about machine learning, right? Or if you just know the very basics of machine learning, if you don't know anything about Bayesian optimization or whatever, you might say, OK, I've got this binary condition, so how about I just train a binary classifier, and I'll just dump in my data, and I'll compute the probability that every point is positive, and then I'll just always evaluate the point with the highest probability of success. Well, it turns out, so like a very natural utility function we might choose for this problem would be to, if I want to maximize the number of hits that I get, I'll just take in my data set, and I'll score my data set according to the number of hits contained inside of it. So I'll just add up all the discoveries I made, and I'll get a unit reward for each of those discoveries. And now, if we choose that utility function, then computing the one-step look-ahead expected improvement in that utility gives rise to this obvious policy of finding the point that with the highest probability of success. And so now we've got like a nice interpretation of this kind of obvious policy. But also a downside of this policy is that it's only looking one experiment ahead. So one-step look-ahead works very well, it turns out, for Bayesian optimization. I'll say more about this in just a second here. But it turns out in active search, it does very poorly. And in fact, we can find constructions of active search problems where myopic strategies perform very poorly. And this is kind of a minimal example that I came up with. So on the right-hand side here, we have a design space that's got 3 points inside of it. The point on the right has probability 99% of being a hit, and the points on the left have 1% probability of being a hit. But the line connecting the 2 points on the left indicates that my model believes that the labels for those 2 points are highly correlated. Let's just say that they're the same. So if one is a hit, they're both hits. If one is a miss, they're both misses. And so now, if I were to perform one-step look-ahead, let's say I can design a sequence of 2 experiments. So if I were to perform one-step look-ahead, I would choose the point on the right. And then no matter what would happen, I would pick one of the points on the left. Whereas it turns out that if you do 2-step look-ahead, so if you, like the optimal policy would be to always label one of the points on the left first. Because one of 2 things can happen. Either you get lucky, in which case the 1% for the attached point in the next iteration will become 100%, which is even better than 99%. Or, probably you won't get lucky. It'll be a 0, but then you've got one evaluation remaining, so you can always go to that point on the right anyway. So it turns out it's optimal to label one of the points on the left, which is, was very surprising to me. Like we have this very tiny example where it is now optimal to choose the point with the lowest probability of success. And in fact, you can, so like this seems like a very simple toy example, but you can take the intuition in this example and you can use it to prove that you can construct active search problems where looking farther ahead can always help you by any arbitrary amount. So if you decide, OK, I think 10-step look ahead is going to be enough, then I, as an adversary, can come along. I can construct an active search problem where if you would just look 11 steps ahead, you would do 10 trillion times better in expectation, or whatever it is. And so we're in this really interesting situation where we can construct explicit examples where non-myopic behavior would lead to huge improvements in performance. OK, so that result on its own is not very useful because it actually, it's interesting, but it's not useful in terms of policy design. If we think back to this problem of like computing this expected utility where I'm trying to design a sequence of experiments, and now I need to reason about the outcome of each experiment and its influence on the design of the next experiment, et cetera, then theoretically I would have to compute this expected utility, which comes from enumerating this giant tree and trying to compute, like, alternatively maximize and take expectations all the way back up. Again, that's computationally totally infeasible. But what makes this computation difficult is all of the interdependence between all of these things. Like the thing that makes this difficult is the fact that I'm thinking about observing an outcome and then designing a new experiment and observing its outcome, et cetera. And there's dependence among all of these steps. One way I could try to get around that is just to assume that there is no dependence. So maybe I can assume that after the first evaluation, everything becomes conditionally independent, which is a crazy idea, but at least it's closer to the true state of the world than to assume that there's no experiments left. So there's an idea that we came up with here to find a efficient but non-myopic policy for active search. And the idea here is that we're going to be, again, enumerating this decision tree. But then after this proposed next experiment is resolved, we're going to simulate that we're going to design all of the remaining experiments in our budget simultaneously in one big batch, and then observe all of their outcomes simultaneously in one big batch. And in particular for active search, because we have these binary rewards and this linear utility function, this computation is very efficient. And it also has the property that it kind of knows about the remaining budget because this batch of experiments will be sized according to the remaining budget. This idea of like doing one step look ahead and then augmenting it with this like batch observation that's going to resolve the rest of the budget has also been used in Bayesian optimization under this algorithm called glasses. And it turns out that it works extremely well on actual active search problems. So I don't have all the details here, but basically we conducted a whole bunch of experiments on drug discovery problems. This plot on the right here is an aggregation of performance on 120 different active search problems that were all related to drug discovery. And what we're seeing is, as a function of the number of budgets, so here we were simulating a sequence of 500 experiments in a space of something like 100,000 or so. And we're seeing the difference in utility, the difference in the number of hits recovered by a myopic approximation. This was actually doing two-step look ahead, versus this efficient non-myopic policy that was trying to look all the way ahead as much as it could to the end of the budget. And what we see is that at the beginning, this non-myopic policy is like dramatically underperforming the two-step look-ahead policy. At one point, like, after 100 evaluations, it's losing by 25 discoveries on average, which is a pretty insane amount. But really what's going on is that that policy is just aware that there's more experiments to come. And so it can spend the beginning of the experimental campaign to kind of do this like targeted exploration of the space. And then as the time is ticking down, it can switch slowly towards exploitation as that budget of remaining experiments gets smaller and smaller. And then at the end, because of what it learned from the early stages of the search, it ends up finding many more discoveries on average than the alternative. And so this was this really beautiful, in my opinion, emergent behavior that came out of trying to inject some non-myopia into this experimental design problem. Now, to say a little bit about theoretical guarantees, so we saw with Bayesian optimization there's very strong theoretical guarantees. And in fact, there's extremely efficient policies for Bayesian optimization that are asymptotically near optimal in the limit as the number of experiments goes to infinity. It turns out for active search, there's extremely strong anti-guarantees. So we've been able to show that there is no efficient policy, so no policy that can be computed in polynomial time in terms of the size of the design space, that can have any constant factor approximation to the performance of the optimal policy, which takes exponential time to compute. And so no matter what crazy ideas you want to try, it doesn't matter if it's Bayesian, it doesn't matter what you do, any efficiently computable policy cannot be near optimal for active search. And so I think there's two things going on. The first is that in Bayesian optimization, there's this natural property of diminishing returns. Like there is some global optimum. And as you continue experimentation, you're going to be making observations that are higher and higher. And then eventually, you kind of reach the ceiling where you can't make any further improvements. And it's that, in my opinion, it's that diminishing returns that makes you able to find efficient algorithms that can nonetheless asymptotically be near optimal. But in active search, because you get this unit reward every time you make a new discovery, this slope can be linearly for a very, very long time. And the way we prove these anti-guarantees on performance is that we construct these active search instances that have this crazy structure where there's like a hidden treasure hidden somewhere. And you have to decode a treasure map to try to find your way to the treasure. And you show that decoding step requires exponential time to accomplish. But that's the other thing going on here, in my opinion. So we also, in deriving guarantees for Bayesian optimization, we make some regularity assumptions. For example, that the objective function has some smoothness guaranteed by a Gaussian process. And probably somebody could come along and find similar regularity conditions for this active search problem, that there's somehow some smoothness property in the labels in order to find situations where you can find efficient but near optimal policies. But thus far, I've not been able to kind of stumble upon the right notion of regularity. That's a challenge for you. OK. I want to talk a little bit about probabilistic numerics. So in particular, is Bayesian optimization even probabilistic numerics? I don't know. Something between 5 and 10 years ago, Philip and I had this long email exchange where we were arguing for pages and pages about whether Bayesian optimization was probabilistic numerics. And at the time, I thought the answer was surely yes. Optimization is a numerical algorithm, and this is a Bayesian realization of that. But now I don't know, right? In this talk, active search, it doesn't feel like probabilistic numerics to me at all. But the way I approach that problem is also just by using Bayesian decision theory to design a sequence of experiments. So I don't know. However, I can identify a couple pointers where ideas from probabilistic numerics have made inroads in Bayesian optimization. The first one is just basically John's talk from this morning. I had this slide, but you don't need to read it. So, naive implementations of Gaussian process inference are very slow. You're going to get like dramatic slowdown after you get 10,000 observations or something like that. And so there's sparse approximations or like iterative numerical methods that we can use to scale to much larger data sets. Again, like the GPyTorch software is doing quite a bit of work to make that accessible to you. And so here, I think thinking about this like notion of computational uncertainty, et cetera, obviously ties into reasoning about the underlying inference underlying this experimental design process. And there's also been some work in Bayesian local optimization methods, which somehow I feel like brings you closer to the like mainstream research in probabilistic numerics. So there's been a lot of effort into deriving Bayesian analogs of like classical local optimization strategies like line search or trust region methods. For line searches, you can use things like Gaussian process surrogates for determining optimal step sizes or for determining optimal search directions. This latter point is actually, I think, quite interesting because you've got this nice property that a Gaussian process is jointly Gaussian distributed with its derivatives or with a gradient. And so you can actually develop like 0th order local optimization methods that will reason about the uncertainty of the gradient, make noisy observations of the function to identify the most promising search directions, and then you can reason about, again, something like a Gaussian process to reason about an optimal step size along that search direction. For trust region methods, you can take like classical trust region methods, which might use like a quadratic surrogate. You can swap in a Gaussian process surrogate that gives rise to this algorithm called Turbo, which has been showing very impressive performance for Bayesian optimization of very high dimensional functions. OK, to mention a couple extensions. So throughout all of this whole talk, I've been focusing on sequential optimization or sequential experimental design, where I measure at one point every iteration. Of course, in practice, in many situations, I could either maybe run like a whole bunch of experiments in parallel, or maybe like a whole bunch of computations in parallel. We can, of course, derive Bayesian optimization routines that work in this kind of batch setting. Decision theoretically, you would want to compute the expected utility of adding a batch to your data set. There's also extensions of like bandit-style algorithms like UCB that have strong theoretical guarantees on their performance. This new idea that comes up once you start designing more than one experiment in parallel is that you want to design batches that trade off exploration, exploitation, and also diversity among the batch members. You don't want to put all your eggs in one basket. Another important extension is multi-fidelity optimization. So it's very common to be able to have multiple methods of making observations. For example, you might be able to do an experiment in a laboratory that might be very high fidelity but very high cost. Or you might be able to do like a computational surrogate, which might be much cheaper but a little bit more noisy. So again, we can kind of jointly model all of these modes of observation and derive acquisition functions that are aware of the relative costs of these different modes of observation and can efficiently operate in this multi-fidelity, multimodal observation regime. There's also methods available for multi-objective optimization. So in something like material science, you might be trading off something like strength versus ductility or something. And rather than choosing a particular trade-off, you might want to map out the entire Pareto frontier of optimal trade-offs. And there are Bayesian methods that will reason about, for example, the expected improvement in the volume of the hypervolume of your Pareto frontier or something like that. OK, so I want to conclude by just highlighting some applications of Bayesian optimization and then some ideas for the future. So Bayesian optimization has seen like extremely widespread adaptation in both chemistry and material science, especially in the past 10 years or so. This is in light of the rise of computational tools in computational chemistry, computational material science, things like density functional theory, molecular dynamics. So Bayesian optimization has been used for like molecular design, optimization of material properties, et cetera. An example of applied chemistry was this paper from Google, where they were trying to optimize the chocolate chip cookie recipe served in the Google cafeteria. So every day they would whip up a new batch of cookies, and they would feed them to the employees, and then they would measure how good they were with a survey. They had this paper at a workshop where they published their optimal recipe. A couple years ago, I had a student make the recipe. He took the picture in the lower right, and he said they were pretty good. It was COVID, though, so I didn't get to try them. I am going to reveal my personal retirement plan if academia doesn't work out, which is that we can use optimization to optimize a beer brewing process. So I want to license this optimization technology to breweries to optimize their beer portfolios. Please don't steal that idea. It's not trademarked or anything. Actually, I asked ChatGPT to come up with punny applications of Bayesian optimization to beer brewing, and it came up with Optim Ale, which is also pretty good. So Bayesian optimization has also been used in physics and biology, things like controlling instruments like particle accelerators, also gene and protein design, also plant breeding, which we started the talk with. There's been an explosion in interest from the machine learning community in the past 10 years in Bayesian optimization, especially in light of the rise of deep neural networks, which have these complicated hyperparameter tuning problems. Philip talked about this this morning. A high-profile use of Bayesian optimization in this context was DeepMind with their AlphaGo program. They actually used Bayesian optimization to tune the hyperparameters of the networks used in AlphaGo. In the Nature paper that they published, they did mention this, but they just cited some paper, right? They didn't give any of the details. A few years later, they published a paper where they detailed the use of Bayesian optimization in AlphaGo, and it actually improved the performance of the platform by something like 100 ELO points, which is a pretty big leap in performance. And this Bayesian optimized version was used in this the famous match. It's also been used across all areas of engineering, like structural engineering, airfoil design, robotics, et cetera. OK, so we've got 4 minutes left. I want to highlight some challenges for the future. The first is that Bayesian optimization enjoys this status where it's basically a pretty mature technology by now. There's this excellent software. People can download it and use it, and people are doing this all over the place, publishing these papers. But something that I find is that every time I collaborate with somebody who's not a machine learning person that wants to use Bayesian optimization, if I spend enough time talking to them, I realize that they have some twist that I did not anticipate. It is very rarely the case that some off-the-shelf algorithm is actually truly what they want. Maybe there's some difference in the utility function, or there's some constraint that I didn't anticipate. And I think there's a lot of room in, it's a big investment, but a lot of room in terms of identifying interesting twists that can then lead to novel research contributions. High-dimensional Bayesian optimization is still a challenge, although apparently Philip's, this survey that was done, I guess a lot of people in industry are only tuning 4 or 5 hyperparameters, so maybe it's actually not that big of a challenge. But in terms of building models that work well in high-dimensional spaces, at least globally, it can be challenging. Maybe local optimization might be one path forward. I don't know. And then finally, again, because Bayesian optimization is such a mature technology, there's been a focus in a lot of Bayesian optimization research to quote unquote take the human out of the loop. We'll just let this Bayesian decision theory or whatever design the experiments. You don't have to be involved at all. But I cannot design an algorithm that has a PhD in material science or a PhD in chemistry or something like this. So then again, they don't have one of my collaborators in material science, they don't have a PhD in machine learning. So how can we build systems that, software systems, that can interact with the user with the massive amount of knowledge that they have in their head about, intuitive knowledge they have about their system of interest, and can we somehow extract information either through interactive visualization or like prompting or preference elicitation or I don't know what, or like up and down voting for proposed experiments. Can we like extract some information that can then be injected into the model or maybe injected into the policy, maybe injected into the choice of utility function that can kind of help the human and the computer collaborate together as a team for the experimental design process. I think you'd have to get, this is like a grand challenge that's going to involve input from cognitive scientists and all kinds of other people. But I think it's the kind of thing that both Bayesian optimization should be thinking about, and also probabilistic numerics, like in terms of building systems that where you can interact with the user enough to know what their goals are, or the constraints that they may exist in a problem, and kind of get it in this kind of natural manner, and then translate it into the mathematical nitty-gritty details. OK, so with that, I'm going to say thank you and take any questions you may have.